All right, it's time to talk about chemical bonding, and before we even get started on this, please know that there are other types of chemical bonds. There are only two types of compounds that form. There are ionic compounds and covalent compounds. Now, ionic compounds, and I want y'all to put this somewhere on your notes paper. Ionic compounds are metals and non-metals, okay? They are when elements, that is the losers and the gainers, come together and form a compound where they exchange electrons, okay? So a few things we're going to write on here. First and foremost, these are our losers. These are our cations, okay? Metals are cations, okay? So you need to know that the metals are cations, all right? Now, the nonmetals, just these, are known as our anions, okay? So something to help you remember this, cations become positively charged, anions become negatively charged. These are our not active nonmetals in ionic bonding. Right here, our anions. A way to help keep cations and anions straight. The T in cations actually looks like a plus symbol, and then some students like to say that anions, the word anions, looks like onions, and they don't like onions, and like that's kind of a negative feeling. Now, if you like onions, that might not work for you. But the one thing I say can work for you is that remembering that cations have a T in it, which looks like a positive charge, okay? So your metals are the ones that lose electrons to become chemically stable. So these lose valence electrons to become chemically stable. These are the ones that gain valence electrons to become chemically stable. Now we are going to mark out the noble gases, because the noble gases are chemically inactive. Something we learned last unit and already were aware of was that noble gases are not reactive. They are chemically stable by themselves. Now, some people ask, what about carbon? You know, carbon only gets involved in covalent bonding, which is nonmetals with other nonmetals. So carbon does not get involved in ionic bonding. Ionic bonding is between a positively charged cation and a negatively charged anion, okay? Now, you might be wondering what's up with the metalloids, okay? So the metalloids are right here. Now, something you need to know about the metalloids is that they are kind of like metals and they're kind of like nonmetals. So they could go either way. Metalloids tend to act more like metals in ionic bonding if they get involved, and then they get involved in covalent bonding with nonmetals as well. So they're kind of they can play either side of the fence. But do know that your metals are your cations. They are the ones that lose valence electrons, and that your nonmetals gain valence electrons. Now, so we have already seen a lot of this material in the last unit. You guys have already been kind of prepped on this. So here are some examples of some positive ions. These are all cations. Over here, these are some of our negative ions. These are our anions. There are very few anions, okay? There's just a few section of nonmetals that get involved in ionic bonding, okay? And there's just not that many of them. Actually, there's only 8 of them, or 9 of them rather, that are active ionic and ionic compounds. So I just want to go ahead and clarify that if you see a positive symbol, like right here with sodium, or just a negative symbol, like right here with chlorine, there is an understood 1 in front of that negative charge. So anytime you see that, where you have just a positive or just a negative written, then it is an understood 1 in front of it, okay? Now, so this is a complementary process. It's important to remember that opposites are attracted. So sodium and chlorine makes what is known as sodium chloride, okay? Sodium loses its 1 valence electron to become positive. Chlorine gains that 1 valence electron, and together their charges cancel each other out, and they are neutrally stable, okay? So now, what we're going to look at is the different ways that you can represent an ionic bond taking place. Now, right here, what we're seeing is a Bohr model exchange, okay? You guys are never going to have to do this. This right here is way too time consuming, okay? But it does still show you how Sodium's one valence electron will come over here and fill up chlorine's its valence shell, and so both of these will end up becoming chemically stable, all right? Metals lose the electrons to become cations. Non-metals gain electrons to become anions. These oppositely charged ions create what is known as an ionic bond, and it is a very strong bond, okay? Now, here is what you guys will have to know how to do, okay? You guys are going to have to be able to show what is known as or what I like to call a Lewis dot electron transfer. And then you also have to show an ionic charge formula, okay? So these are two different ways to represent a satisfied neutral ionic compound. So right here, this is what is known as a Lewis dot electron transfer, and this right here is an ionic charge formula. One, you will prefer probably one over the other, but you need to know how to do both, okay? Because ultimately, you will eventually have to drop doing this one and always do the ionic charge formula. All right, so let me give another example. This is where you're going to have some open space on your paper, and you can do some examples with me. So let's say we're going to take magnesium and fluorine, okay? Magnesium has 2 valence electrons. Fluorine has 7, okay? This is what we would call an imperfect ratio because fluorine needs 1 more valence electron to become stable, but magnesium has to lose that other electron to become stable. So that means that you have to have another fluorine ion to donate to. Now what this means is that your chemical formula for this would be 1 magnesium ion, that is 1 cation, for every 2 fluorine ions have to come together in order for this compound to be formed and chemically neutral. You would never write this. This doesn't exist. Magnesium fluoride only forms in a 1:2 ratio. 2 fluorine ions, that is 2 fluorine anions for every 1 magnesium cation to create stability for both of the atoms in an overall neutral charge, which is what I'm going to show you next. So the ionic charge formula to me is quicker, it's easier, it's going to be the way that most of you guys are going to have to adopt doing this, all right? So in an ionic charge formula, you simply write the 2 elements. Okay, so these are the Lewis dot electron transfers in the ionic charge formulas. In each one of these, you can see that the elements have lost the electrons they needed to become stable, and the charges are equal. Now, I didn't realize my video paused, so I'm going to redo this one right here with you guys, since I didn't realize that it had paused. All right, so what I was showing was with the Lewis dot transfer, lithium has 1 valence electron, oxygen has 6 valence electrons. Lithium only has 1 to donate, but oxygen needs 1 more here. So you would need another lithium ion to transfer over here. Now, in this case, you need 2 of your cations, 2 of your lithium ions for every 1 oxygen. So the formula would be Li2O. This subscript represents the number of ions needed in the compound to make it chemically stable. Now, it also represents the number of ions needed to create an overall neutral charge. And so we can show that with the ionic charge formula, where we see that lithium with a 1 positive charge in group 1 and oxygen with a 2 negative charge in group 16, they are not equal. They have to be. You cannot do anything about this 2. You cannot reduce it down to a 1, but you can work up this 1 to a 2 positive charge by just writing another lithium ion. So you can see 2 positive charges cancels out 2 negative charges. And so there again, we have that Li2O, and you can see that it creates an overall neutral compound. So these are 2 different ways, Lewis dot electron transfer and the ionic charge formula, of supporting how ionic compounds complement is a complementary process of electron transfer and exchange between two oppositely charged ions. Now, there's one more that I'm going to do. I'm going to pause the video and do with you guys in class. All right, so oftentimes there are some that might be a little more difficult doing the Lewis dot diagrams, like aluminum with oxygen. Right here, it's like you can't make a 3 a 2 and a 2 a 3. So you have to come up with the least common multiple between 3 and 2, which is 6. Aluminum can become 6 with a 3 positive. Oxygen can become 6 with 3 total 2 negative charges. So unlike over here, where all we had to do is add one additional ion of either a cation or anion to make them equal, sometimes you have to work them up to the least common multiple, which in this case would be 6 positive charges to 6 negative charges, and they would cancel out. And so that would give you an overall formula of Al2, that's 2 aluminums, for every 3 oxygens. We will pick up on the properties in class or in another video lesson tomorrow.